Yeah, so our next speaker is Elena Hassinger from TU Dresden, and she's going to be talking about controlling two-phase superconductivity in cerium-rhodium arsenic. The TC is extremely low, right, in this stuff, right? It's like
Yes.
what's a TC? What's a TC? I can remember.
0.3 Kelvin.
0.3 Kelvin. Wow. How do you? Okay. So you have to have a special technique, to measure all the properties such low temperature.
Can be challenging, but dilution fridges are fine.
Yeah. Okay. So it's all yours. Thank you.
Okay. Thank you for the invitation to this nice workshop. And yeah, I'm covering the heavy fermion superconductors that we just saw theoretically. So before I start, I would like to thank my group and my collaborators. So in my group, I will show work by Javier Landaeta. And in the second half of my talk, I will show some pressure work. And that has been carried out mainly by Michael Pfeiffer and Konstantin Semenyuk. And I want to highlight also some people in the Max Planck Institute in Dresden, where I was before, and namely Manuel Brando, who is responsible of the specific heat measurements, and also especially Sung-Young Kim, who grew the samples, and he discovered the superconductivity in this material, and also the anisotropic who grows the samples, and he discovered the superconducting state in this material. And I also saw that in the audience we have Philip Bryden, who is one of my theory collaborators, and it's a pleasure to see you here. Okay, so this talk is about a really amazing phase diagram in this material that you see here on the right, and you see that there are two superconducting states when you apply the magnetic field along the crystallographic z-axis. And there are only two other well-confirmed multi-phase superconductors, which are these two uranium heavy fermion compounds, so uranium platinum 3 and the more recently discovered uranium ditelluride, which is also very interesting for a field-induced superconducting state. So in both of these materials, the appearance of multiple superconducting phases has been interpreted as a sign of spin triplet pairing. And this was following the ideas of superfluidity in helium-3, where you have three different superfluid states that can be identified with different different functions in the spin part of the Cooper pair wave function. In this material, however, cerium-rhodium to arsenic-2, we have a different way of understanding the two superconducting states, and it's based on the locally non-centrosymmetric crystal structure, as we believe. So I'm going to tell you how this works. So in my talk, I want to explain how we currently understand the phase diagram in this material, and I will tell you about the role of the crystal symmetry, and then I will cover the role of other orders, because this material is not only superconducting, but also has other ordered states. And the underlying question of my work at the moment is, why do we find this phase diagram only in this material so far? Although the crystallographic structural properties are also present in other materials. Okay, so here's the crystal structure of this material, and it's not the normal 1-2 structure, it's the calcium beryllium 2 germanium 2 type structure. And in this structure you have two cerium atoms per unit cell, and they have an alternating environment. So you can see that this cerium has a rhodium layer above and arsenic layer below. And the next cerium has an arsenic layer above and the rhodium layer below. And so you lack mirror symmetry, and that's how you can get Rashba spin orbit coupling at the cerium position, which alternates the sign when you go from one cerium layer to the next. So if you imagine that you have a superconducting pairing dominantly in this layer, then this pairing would be like in non-centrosymmetric superconductors. So where you can have effects like singlet and triplet mixing, for example. However, in this material, parity is well defined because it is overall a centrosymmetric structure. So you can see that by knowing that the inversion center is here in the middle of the line connecting the two cerium atoms. Okay. So here's the experimental phase diagram for both magnetic field directions. This is the one you've already seen. And there's several remarkable things. Tc is low, as you've heard. It's just 0.3 Kelvin. But the critical field is extremely large, so strongly exceeding the Pauli limit with 14 Tesla. And then, of course, there's this strange kink and the phase transition between the two superconducting states that we detect in susceptibility, in magnetization, and also in magnetostriction. For fields in the plane, the phase diagram looks more standard. As you see here, just one superconducting state, but still the upper critical field is very large, although it's much lower than along C, but it still strongly exceeds the Clarkson-Chandrasekhar-Pauli limit. Okay, so this strong anisotropy with large critical fields along the Z-axis is very well known for non-centrosymmetric superconductors. And to show you an example, here's data for cerium rhodium silicon 3 at 2.6 GPa, where Tc is the largest in this material. And there you have a similar behavior where critical fields along the C-axis seems to be only orbitally limited and very large. And for fields in the plane, we have this strongly Pauli limited feature, but the Pauli limit is enhanced compared to the BCS Pauli limit. Okay, and so here on the right, we have compiled a collection of a number of unconventional superconductors, very famous ones, where we plot the critical field normalized by Tc versus Tc. And we differentiate fields along C-axis and fields in the plane. And in red are all the non-centrosymmetric superconductors. So you see they all fall into this scheme of this strong anisotropy. And cerium rhodium 2 arsenic 2 also falls into this scheme. So this makes us believe that the local non-centrosymmetry and the Rashba-spin orbit coupling plays a fundamental role in this material to explain the phase diagram. Okay, and just to give you a kind of physics behind it, in non-centrosymmetric materials, this has been calculated. So you have a Rashba spin split Fermi surface where spins are locked to the momentum as shown here. And then only certain types of Cooper pairing remain when you turn on the Rashba spin orbit coupling. And Frigeri and Siegrist and co-workers have calculated the Pauli limit for different values of the Rashba spin orbit coupling, and you can see that it's strongly enhanced. And this is for fields along C, but also a bit reduced for fields in the plane. So that's how we currently, or how you understand the anisotropy of the critical fields in non-centrosymmetric systems. However, in non-centrosymmetric systems, there is no kink anywhere. So this locally non-centrosymmetric feature must play a role. And there has been number of papers on a model system by Janase and Siegrist and co-workers starting already over 10 years ago, where they looked at systems where you have superconducting layers separated by normal layers. And this was inspired by experimental work by the Matsuda group, as for example in this paper, where they found very large critical fields. And so they considered that in the uppermost and lowermost layer of the superconductor, you break inversion symmetry locally, because here you have a different neighbor than here. And so you get Rashba spin orbit coupling term, which has an opposite sign between this layer and this layer. And then they also included some coupling between these layers. And they find that then you can have two options for the superconducting state. One is the even parity state. And here parity is also well defined because overall this is also a centrosymmetric system. And for the even parity state, the superconducting gap, so here they only look at the singlet component, has the same sign on both layers. And there's also an odd parity state where the sign changes between the layers of the superconducting gap. And they predict a phase diagram, temperature and field, where when you start with an even parity state at low fields, this is Pauli limited and so suppressed. And at some point, you will have a switch, a first order transition to an odd parity state, which survives up to high fields. Okay, and that's actually how we understand our phase diagram. And the reason is that our system, although we start from the bulk crystal structure, is very similar. And we can even write down a Hamiltonian, starting with all allowed terms in the local symmetry of the cerium. And we end up with a very similar model as before. And so we have these two even and odd parity superconducting states. Okay, so as I just briefly mentioned before, there are a number of unconventional superconductors which also have the structural properties of two inversion partner atoms in the unit cell. So there are these uranium-based unconventional superconductors and also cuprates and single-layer iron superconductors. And this was recently very nicely described by in these two theory papers. And in all those materials, apart from cerium, rhodium to arsenic 2, it's not yet clear how this structure plays a role for the superconducting state. What we know from our studies is that the structure is not enough to get the two superconducting phases. So what we did is we studied this sister compound, lanthanum rhodium to arsenic 2. So it has no F electrons and is a weakly correlated material. So the gamma is only 10 millijoule per mole Kelvin squared. And luckily, it's also a superconductor with a very similar TC of also roughly 0.3 Kelvin. You see specific heat, AC susceptibility, and resistivity. But the upper critical fields are very low. So here, this is millitesla and not Tesla. And they are purely orbitally limited. And this is, now the open question is, apparently we need the correlations, but maybe we only need the correlations to enhance the effective mass and to bring up the upper critical field so that the Pauli physics becomes visible. Okay, now cerium, rhodium to arsenic 2, back to our starting material, has another phase transition that occurs above the superconducting state. And we call the phase transition temperature T0 because currently we don't know what the order parameter is. And in the first samples, it showed up as a small hump here above the anomaly to the superconducting state. And this has a very low transition temperature of 0.5 Kelvin also. So there are signs that this system is close to a quantum critical point, which is the low transition temperature, but also the strong increase of the specific heat, C/T, as we decrease temperature with this strange power law, and a very large value of the effective mass here. Okay. So we don't know, there's no microscopic measurement yet of the order parameter, or at least at this temperature, T0, you will see later. And I'm going to show you what we know from bulk measurements. So here's the susceptibility as a function of temperature and measured from DC magnetization in green and from AC measurements in blue. And you can see that across the phase transition, there's no clear anomalies. So that's why we thought either this is a very weak magnetic transition or it's a non-magnetic order. And here's again the anomaly in the specific heat, and which is small. But then in the thermal expansion, at least along the C-axis, there's a rather pronounced anomaly. So we have clear thermodynamic evidence that there are two phase transitions. And in resistivity, it shows up as an upturn. This is work by Sanu Mishra and co-workers from Philip Ronning's group. And this looks like a charge density wave transition or spin density wave transition. Okay, and the behavior in magnetic field is very anisotropic of this phase, so we call it phase 1. When we apply a field along the z-axis, it's suppressed, and it's suppressed at a field larger than this transition between the two superconducting states, which is roughly at 4 Tesla. So we follow this line, and it seems to meet here at roughly 6 Tesla. And maybe I just should briefly mention that there's still a bit of a debate if this line is not meeting the H-star line. But in our measurement, it looks like this. When we apply a field in the plane, then this transition temperature remains almost unchanged up to 8 Tesla. Then there's a phase transition, first order, to yet another state, and then the transition temperature increases. And here on the right, I don't have time to go through this, but there's data supporting this line here. Okay. And to make the situation even a bit more complicated, there's also evidence for an antiferromagnetic order, but this occurs at lower temperatures, so roughly at Tc. And this evidence comes from NQR and NMR, where they see a broadening of the one of the arsenic lines. And this broadening sets in roughly at the bulk Tc of that sample. Now the question is there a third order parameter, so the T0 order, superconductivity, and antiferromagnetism? And then in bulk measurements, we only see 2 transition temperatures. So is that because 2 of the 3 order parameters accidentally have the same critical temperature? These are open questions. What I can say from our measurements is that we don't see a splitting of any anomalies when we apply magnetic field or pressure. But, and so we do not have any information on this state from our bulk measurements. That's why I'm not going to say anything about them from now on. And it seems that there are new results from specific heat on high quality samples by the Kasurowski group from Poland, where they claim they have a new phase diagram, and this is an accepted paper, so far there's only the abstract visible. But because there's this antiferromagnetism somewhere, there was also a suggestion that the H-star transition is actually combined with a magnetic transition and not this even and odd parity. So that's also a debate. I want to show you here that the sample quality has improved since the beginning. So these were the first measurements on first batches. And now we have 2 new generations of crystals which have clearly increased transition temperatures for both Tc and T0, and also much sharper anomalies. And the quality of this sample is the same as the one from the Poland group, where these 2 papers have been published. The RRR is still not very good in these samples. It's only 3 in the best samples we have. Okay, so what we did now, and what I'm going to show you for the rest of the talk, is we carried out resistivity measurements under pressure, because pressure is a very effective tuning parameter in heavy fermion systems. And we try to find out what stabilizes the 2-phase superconductivity and what's the relation to the proximity to other orders, and how do correlations influence the 2 phases. And we have put 2 papers on the archive that cover the normal state and the superconducting state under pressure. And here's a summary of those results. So first, I show you data resistivity versus temperature at 6 Tesla, where the superconducting state is suppressed, so we are here. And the T0 is nearly unchanged. And so we observe T0 as this kink in the curve. And you can see that by increasing pressure, it's strongly suppressed. And this is confirmed by specific heat measurements shown here as a function of temperature, where we have this nice T0 anomaly in zero pressure, and then it's strongly suppressed in very small pressures of 0.1 GPa. So now please look here first on the right. We have this T0 suppression with pressure that you see here, and there seems to be a quantum critical point at roughly 0.5 GPa. Now, we measured the superconducting transition in zero field, and these are all the pressures. So pressure increases like this, and we go up to 2.7 GPa, and TC is roughly suppressed by a factor of 2. And then we can trace the phase diagram at zero field, shown here on the left, where you see that the superconductivity basically evolves as a dome around this critical pressure. And just as a side remark, we've measured 4 samples in our study as a function of pressure, and we did not confirm this decrease of TC that was reported in CeRh2As2's paper. Okay. So then if there's a quantum critical point, we should see this in the temperature dependence of the resistivity, and that's what we studied here, or what we show here. So here's a pressure of 0.7 GPa, which is very close to the quantum critical point. And you can see that the resistivity is linear down to the lowest temperature we could measure. And then as we increase pressure, similar to what Stephen Hayden showed, is with doping. So here we start to develop a curvature, and the exponent grows, this is shown here in green, to around 2. So it becomes Fermi liquid-like at the highest pressures. At the same time, the residual resistivity decreases. This is shown here in violet. And the A coefficient, which we analyzed in this way, because we have this open exponent, shows a peak as it should when we reach a quantum critical point, and then decreases, and this indicates a decrease of correlations with pressure. Okay, and now I will, for the rest of the time, show you the phase diagrams along the 2 crystallographic directions as a function of pressure. So first, for fields in the plane, and pressure is increased like this. So TC decreases, as we saw before, but the upper critical field for in-plane fields first increases and then decreases. And this is what is shown here as a function of pressure. And this peak is again very close to the critical point that was roughly at 0.5 GPa. And this is actually something we also know from other heavy fermion systems. And I have picked out here just graphs for cerium, iridium, silicon-3, where it's a quite extreme case. So what you see is that in zero field, the magnetic phase usually stops and you cannot follow it inside the superconducting state. But if you apply field to suppress superconductivity, you can follow this line, and then you find that the upper critical field peaks roughly at the pressure where this line goes when superconductivity is suppressed. And that's what we see in our material. So here is normalized T0, normalized critical field, and this peak is very close to the quantum critical pressure. So the way this is usually understood is that we have an enhanced coupling between the pairing mediating fluctuations, which are unknown in our material so far, and the electrons near the quantum critical point, and this enhances the upper critical field. Okay, now the phase diagram along the z-axis looks like this. Here, TC is decreased again, as it should, and the upper critical field monotonically decreases. And in this superconducting state 2, so for the data above the kink, above H star, we can fit this curve with a normal orbital limit. so pure orbital limit. And so this then, the extrapolation to 0 temperature is the orbital limit, and this strongly decreases. But you can also analyze the orbital limit by taking the slope here near TC, and we compare the two, and this is shown in this graph. So the orbital limit that we take from the slope is in violet, and the orbital limit we get from the data in the 0 temperature limit is the blue one, and they track each other quite nicely. And so that's why we think that this suppression of the critical field is only due to a suppression of the effective mass, so a decrease of the correlations. Okay. What you see also in this data is this nice kink that occurs at H star, and the kink we can follow up to the highest pressure of 2.7 GPa. Here's a zoom, so you can clearly see the kink, and it strongly moves down in field. So this is what's shown here. It goes from 3.8 Tesla down to 0.3 Tesla. Okay, so what we know from before is that T naught is suppressed at half a gigapascal, but the two superconducting states survive up to the highest pressure we measured, so 2.7 GPa. And this means that the T naught cannot be the origin of the H star transition, which is claimed by some of our colleagues. Okay, and another important finding is here on the summary slide. If you compare just the superconducting phase diagram in 0 field and in the highest pressure, you can see that the superconducting state 1 compared to superconducting state 2 is strongly shrinks. Okay, so it becomes less and less stable with pressure. And so it might be that at some pressure, which we couldn't reach in this measurement, we would get the superconducting state 2 even in 0 magnetic field, which it would be nice. It would be an odd parity state in 0 field. Okay, and so that's the end of my talk. Thank you.
Yes, thank you very much. Very interesting. Yeah. So let me ask you sort of a first question. So are there actually, you say that system can potentially be a spin triplet? Are there any information on what is a spin fluctuation doing? Is it close to a sort of anti or ferro or wave vector or any information?
Okay. So there's no publication on spin fluctuations yet. I've heard that Colin Broham is working on this, but also I haven't seen any results yet. The problem for neutron scattering, at least for us, is that the crystals are still quite small. Mm-hmm. And so we would have to make a huge mosaic. But just to say one thing, you said spin triplet, but this is actually pseudo spin triplet because it's the odd parity comes from this interlayer degree of freedom, which is then the pseudo spin. Mm-hmm. And in that pseudo spin, it's a triplet. The pairing itself can be dominantly singlet pairing, but still you can have these two superconducting phases by the change of the gap. Okay. The change of the sign of the gap between the layers. Yeah.
Yeah, Elena, nice talk. So this pressure tuning is fascinating. I was wondering whether there's any information about the lower temperature magnetic order, whether that's also being tuned by pressure?
Yeah, that's a very good question. And to answer this, you would have to do NMR under pressure. And I'm sure that Kenji Ishida is doing these measurements, but I don't know the results.
Okay. It would be very interesting to see whether it's like something like there are these quartet materials like CM3, palladium-20, silicon-6, where the anti-ferromagnetic order and some other order, like a quadrupolar order, can be tuned sequentially, and maybe there's even quantum criticality that's associated with each or both channels. So it will be very interesting.
Yes. Yes.
Yeah. Okay.
Indeed.
Thank you.
Yeah, thank you. Any other question? Okay. Yeah. Yeah, please.
Hi, Elena. Thanks for the nice talk. I have a two-part brief question. Can you speak about the disorder dependence of this odd parity state? And do you know anything about the where you say you speak of it as a pseudo spin triplet? You say something about where the nodes of this on the Fermi surface are expected to be?
Okay, about the nodes, I don't know. Yeah, so I don't know. And I don't know if Philip Bryden knows better than me. He can comment. And then what was
sorry, it was about the disorder dependence. You
Ah,
have
the disorder.
several samplings with different RR.
From experiment, we see basically that the critical fields scale with the ratio of the TCs. So, you know, with better quality, we get higher TC, and we also get slightly larger critical fields, but it scales with this, yeah,
Okay,
to what
Philip?
we know now. Yeah. Okay,
Philip might have an answer for you.
Philip wants to say something.
Hi. I just wanted to follow up on that question. The nodes would only necessarily have to be at time reversal invariant points so it would be a bit like a helical p-wave state. However, in some sense, in this staggered singlet perspective on the second superconducting state, we would essentially be, in some sense, it's inheriting some of the properties of the zero field singlet state. So if the zero field singlet state, say, was D wave, there might be a D wave like modulation also on the high field singlet state.
Yeah, and just to follow up on this from experiment, we don't have lots of information on the gap structure yet. So we have done thermal conductivity measurements, but on the very first generation samples, and there, the signal is not clear. And we know from specific heat that the gamma term goes down, the zero temperature extrapolated gamma term goes down with crystal quality. So we still think we cannot really analyze the temperature dependence. And then from μSR measurement, this is unpublished work, but Sung-Jung has presented it before, that there seems to be a full gap. But yeah, that's about